Pluto is a distant and cryptic, modest planet that was once part of our nearby planetary system. However, recent revelations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggest that this cold world could be on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a colossal event? Are we witnessing a fascinating cosmic peculiarity, or is there something more to this impending celestial collision? Join us as we explore the possible outcomes of a Pluto-Neptune crash. Pluto, a former planet that was downgraded to a dwarf planet partly due to its unique orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading researchers, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both sounding the alarm about a potentially hazardous collision between these two planets, which could pose a tremendous threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, and since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, measured at 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying expectations based on their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike other planets whose orbits lie mostly near the ecliptic plane, Pluto's orbit stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like predicting their future positions based on their starting points and mutual gravitational pulls. For Pluto, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. Terms like azimuthal libration and degree libration, along with the VSK oscillation, are key to understanding this puzzle. According to astrophysicists, azimuthal libration ensures that whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Degree libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is far above their orbital plane, providing additional protection from potential collisions. Another critical factor is the VSK oscillation, named after three researchers, Vezel, Zell, and Kai, who studied the gravitational interactions of celestial bodies. In Pluto's case, the VSK oscillation helps maintain its orbit stability despite its apparent irregularity. This oscillation demonstrates that even though space might seem chaotic, certain patterns and rules keep everything in order. These mechanisms ensure that Pluto doesn't collide with Neptune or deviate from its path. The three-body problem is central to understanding how these orbits evolved due to the gravitational interactions between objects. This research not only helps us understand Pluto and our solar system, but also distant worlds and their stars. Mathematical simulations in the late 1980s revealed that, despite its chaotic properties, Pluto's orbit remains stable over extremely long timescales, effectively maintaining order amid the chaos. Recent computational insights have shed light on how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. For every 2 orbits Pluto completes around the Sun, Neptune completes 3, creating a stabilizing relationship. However, Neptune isn't the only player. Jupiter's gravity also plays a significant role, and Saturn adds further stability. These forces together ensure Pluto's path remains consistent, even over thousands of years. These phenomena are essential for maintaining order and stability in space. Without them, the solar system would be far more chaotic, with bodies like Pluto potentially colliding or being ejected from their paths. Understanding Pluto's orbit provides a clearer picture of the dynamic nature of the solar system. Even seemingly unstable orbits can reach equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Astrophysicists like Neil deGrasse Tyson, known for his role in redefining Pluto as a dwarf planet, emphasize the evolving nature of celestial mechanics. The case of Pluto reminds us of how much remains to be discovered about our universe and the critical role of continuous observation and study in unraveling its mysteries. Tyson views Pluto's reclassification not as a demotion, but as a necessary adjustment in our growing understanding of the solar system's complexity. He emphasizes that new discoveries demand a reevaluation of old concepts. This perspective underscores the dynamic nature of science, where classifications and theories evolve as our knowledge expands. The broader implications of studying Pluto's orbit extend beyond our solar system. Understanding the gravitational interactions and stability mechanisms at play provides insight into exoplanetary systems, distant worlds orbiting other stars. These principles help astronomers predict the behavior of exoplanets, their potential for stability, and even the likelihood of habitable conditions. The ongoing research into Pluto and Neptune's relationship also highlights the importance of advanced simulations and computational models in modern astronomy. Virtual simulations allow scientists to test different scenarios, tweak initial conditions, and observe potential outcomes over millennia. These tools are invaluable in understanding chaotic systems, like Pluto's orbit, and predicting long-term cosmic events. Despite the current stability, the question remains: could future perturbations, perhaps from an external force or an unaccounted object, disrupt this delicate balance? The gravitational influences of other celestial bodies, potential encounters with rogue planets, or even passing stars could introduce variables that might alter Pluto's trajectory. These scenarios, while unlikely in the near future, cannot be entirely dismissed. Moreover, the study of Pluto's orbit offers a reminder of the interconnectedness of celestial mechanics. Each planet, moon, and asteroid plays a role in the delicate dance of our solar system. The stability of one object often depends on the gravitational influences of others. This interconnectedness ensures that even a small change in one part of the system can have far-reaching consequences. Looking forward, continued advancements in observational technology, such as next-generation telescopes and space missions, will provide even deeper insights into Pluto's behavior and its interactions with Neptune. Missions like the New Horizons spacecraft, which provided the first close-up images of Pluto, have already revolutionized our understanding of this distant world. Future missions could offer even more detailed data, helping to refine our models and predictions. In the grand scheme of cosmic events, the potential for a Pluto-Neptune collision remains a fascinating but distant possibility. The safeguards built into the universe's gravitational mechanics, from librations to oscillations, illustrate the incredible complexity and precision of our solar system. As we continue to explore and understand these celestial dynamics, each discovery brings us closer to unraveling the mysteries of the cosmos and our place within it. Ultimately, the case of Pluto serves as a powerful reminder of the ever-evolving nature of science. What we know today may be refined tomorrow as new data and insights emerge. The universe is a dynamic, ever-changing entity, and our quest to understand it is an ongoing journey, one filled with surprises, challenges, and endless wonder.